Welcome to this walkthrough of problem number 1145, binary tree coloring game. In this session, we'll explore the problem's key concepts, analyze the approach, and break down the solution step by step. Let's dive in and see how player 2 can secure a win using strategic moves. In this problem, we are working with a two-player game played on a binary tree. The players take turns coloring the nodes of the tree in their respective colors, red for player 1 and blue for player 2. The game starts with player 1 coloring a specific node, identified by the value X, red. Player 2 then chooses a node to color blue, and the turns alternate from there. A key rule is that no node can be colored more than once. The game ends when there are no more uncolored nodes available for either player to choose. The winner is the player who has colored more nodes in their color. Your task is to determine if player 2 can guarantee a win assuming that both players play optimally. To solve this, you are given the root of the binary tree, the total number of nodes n, and the value of the node x that player 1 colors first. The output for this problem is a Boolean value, either true or false. If player 2 can guarantee a win by playing optimally, the output is true. Otherwise, it is false. Let's look at an example to understand this better. Consider a tree with the structure given as an array 1, 2, 3, 4, 5, null, 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 6, 7, where n is 7, and player 1 starts by coloring the node with the value 2. In this case, the output is true, meaning player 2 has a guaranteed winning strategy. The explanation of why this strategy works is shown next. Here's the tree structure based on the given input. The tree has the root node 1, with its left child as 2 and right child as 3. Node 2 further has children 4 and 5, and node 5 has children 6 and 7. Player 1 begins by coloring node 2 red. To maximize their chances, player 2 can then color the root node 1 blue. This move effectively splits the tree into two subtrees, one rooted at 3, containing only one node, and another rooted at 2, which contains all other nodes. By making this strategic move, player 2 ensures they control the larger portion of the tree, guaranteeing that they will color more nodes than player 1, regardless of further moves. In another example, consider a smaller tree represented as 1, 2, 3, where n is 3, and player 1 starts by coloring the root node 1 red. The tree structure is simple, with 1 as the root and 2 and 3 as its children. Player 2 now has to choose between coloring either node 2 or 3 blue. However, no matter which node player 2 chooses, player 1 will always be able to color the remaining child node in their next turn. This ensures that player 1 always controls more nodes than player 2. Hence, the output is false, as player 2 cannot guarantee a win in this scenario. The problem also introduces some constraints and edge cases to consider. The number of nodes, n, is between 1 and 10,000, and every node has a unique value ranging from 1 to n. Importantly, x is always a valid node value within this range. For edge cases, if n is just 1, player 1 wins automatically since there are no other nodes for player 2 to color. In highly unbalanced trees, where nodes form a single branch, player 2 must be cautious in selecting nodes to optimize their advantage. If player 1 starts by coloring the root, player 2 can strategically split the tree by coloring one of the root's children. Conversely, if player 1 colors a leaf node, they gain minimal advantage, giving player 2 a better chance to control more nodes. These considerations are crucial in determining the outcome of the game when both players play optimally. To solve the binary tree coloring game, we first need to understand the key dynamics at play. The game begins with player 1, who colors a specific node, x, effectively splitting the tree into 3 regions. These are the left subtree of x, the right subtree of x, and the rest of the tree, which excludes x in its subtrees. The objective for player 2 is to maximize control over the nodes by strategically coloring an uncolored node on their turn. The player who controls more than half of the total nodes wins. One straightforward way to approach this problem is through exhaustive simulation. In this brute force method, we simulate every possible move player 2 can make after player 1's turn, and for each move, calculate the number of nodes player 2 can potentially control. This allows us to determine whether player 2 has a winning strategy, but it comes at a significant computational cost for larger trees. To implement the brute force approach, we would follow these steps. First, traverse the entire tree to construct an adjacency list that captures all possible connections. Next, for each potential move by player 2, calculate how many nodes they would control after that move. Finally, we compare player 2's total controlled nodes to half the total number of nodes in the tree to check if they could secure a majority. However, this method has a time complexity of n squared, as we are simulating multiple moves and recalculating controlled nodes each time. This makes the brute force approach impractical for trees with a large number of nodes, say 10,000 or more. To address this inefficiency, we turn to an optimized solution that uses divide and conquer and subtree size calculations to achieve the same result in linear time. The optimized solution simplifies the problem by using a divide and conquer strategy. First, we find the node X that player 1 has chosen. Then, using a post-order traversal, we calculate the sizes of the left and right subtrees of X. Once we have these sizes, we compute the size of the remaining part of the tree by subtracting the sizes of the left and right subtrees, along with X itself, from the total number of nodes. This gives us three distinct regions: the left subtree, the right subtree, and the remaining tree. To determine if player 2 can win, we identify the largest of these three regions and check whether it contains more than half of the total nodes. This approach has a time complexity of n, as it requires only a single traversal of the tree. It is both efficient and precise, avoiding the overhead of simulating every possible move. When we compare the two approaches, the brute force method and the optimized solution, the differences are clear. The brute force method, with its n squared complexity, is computationally expensive and not feasible for large trees. In contrast, the optimized approach, with its linear time complexity, is scalable and handles large input sizes efficiently. Both methods use h additional space, where h is the height of the tree, due to the recursion involved in traversing the tree. The optimized solution stands out because it captures the essence of the problem, focusing on the sizes of the subtrees to make the calculation both elegant and efficient. This simplicity, combined with its scalability, makes the optimized approach the superior choice for solving this problem. The binary tree coloring game is a strategic problem involving two players aiming to control the majority of nodes in a binary tree. Player 1 starts by selecting a node, X, and coloring it red. Player 2 then chooses another node and colors its connected nodes blue, attempting to maximize their control of the tree. The winner is determined by who controls more nodes after both players have made their moves. To solve this problem, we need to evaluate whether player 2 has a winning strategy, given the tree structure and the initial choice of X by player 1. The first step in solving this is to parse the input and represent the tree efficiently. Using an adjacency list, we can store the tree structure with each node as a key and its children as values. This representation is both space efficient and enables us to traverse the tree easily to calculate important metrics, such as subtree sizes. Once we have the tree representation, the next step is to identify how player 1's choice of node X divides the tree. The selection of X creates three distinct regions: the left subtree rooted at X's left child, the right subtree rooted at X's right child, and the rest of the tree, which we call the parent subtree, connected to the parent of X. These three regions are mutually exclusive, and player 2's goal is to strategically choose one of them to maximize their control. To analyze this, we calculate the size of each of these regions. Using a depth-first search starting at X, we determine the size of the left and right subtrees. For the parent subtree, we calculate the remaining nodes outside of X's subtree. These sizes are critical for determining whether player 2 can gain control of more than half of the total nodes in the tree. With the subtree sizes calculated, we can now analyze the control strategy. If player 2 selects one of the three regions, they gain control of all the nodes in that region. Player 1, in turn, retains control of the nodes in the other two regions. Since the total number of nodes in the binary tree, denoted as n, is fixed, player 2 will win if the size of their chosen region exceeds n/2. To determine this, we compare the sizes of the left subtree, the right subtree, and the parent subtree. If any of these sizes is greater than n/2, player 2 has a winning strategy. Otherwise, player 1 retains control of the majority of nodes and wins the game. Finally, the result of the algorithm is output is true if player 2 can win and false otherwise. This problem offers several key insights that simplify our approach. First, the division of the tree into three distinct regions by player 1's choice of X is central to the strategy. It reduces the problem to analyzing the sizes of these regions. The optimal strategy for player 2 is to select the largest of these regions to maximize their control. Certain edge cases also need to be considered. For example, in a single node tree, player 2 cannot win because there are no other nodes to control. In a perfectly balanced tree, the symmetry of the structure requires careful analysis of subtree sizes. In highly skewed trees, one subtree may dominate the others, making the optimal choice more obvious. To implement this efficiently, we rely on two main data structures, an adjacency list to represent the binary tree and a DFS mechanism to compute subtree sizes. This ensures the solution is both space-efficient and computationally efficient. The solution to this problem involves a few key operations and optimizations. First, the depth-first search calculates subtree sizes in linear time since each node is visited exactly once. This makes the operation highly efficient. Next, comparing the three region sizes is a constant time operation, as we only need to evaluate three values. To further optimize, we avoid redundant computations by storing the subtree sizes after calculating them, thus reusing results instead of recalculating. Overall, the algorithm achieves a time complexity of O(n) due to the single traversal of the tree, and the space complexity is also O(n) to store the adjacency list and recursion stack. This ensures that the solution is scalable even for larger trees. This Python implementation solves the binary tree coloring game problem by calculating the size of the subtrees rooted at the node chosen by player 1 each x, and determining if player 2 can control more than half the nodes by choosing strategically. Explanation. 1. Helper function, count_nodes. This recursive function calculates the size of a subtree rooted at a given node. If the current node is none, it returns 0. Otherwise, it recursively sums the sizes of the left and right subtrees and adds 1 for the current node itself. If the current node is the one chosen by player 1 x, it stores the sizes of its left and right subtrees in self.left_size and self.right_size. 2. Tree traversal. The count_nodes function is called on the root of the tree to determine the total number of nodes in the tree, total_nodes. During this traversal, it also calculates the sizes of the left and right subtrees of x. 3. Parent side size. The size of the subtree containing nodes not in player 1's chosen subtree is calculated as total_nodes, self.left_size plus self.right_size plus 1. This represents the nodes on the parent side of x. For a winning condition, player 2 wins if they can control more than half the nodes. This is checked by comparing the maximum of the three regions player 2 can choose, left subtree, right subtree, parent side, with n//2. 5. Return statement. The function returns true if player 2 can win, otherwise false. Complexity. Time complexity, O(n), where n is the number of nodes in the tree, since each node is visited once during the traversal. Space complexity, O(h), where h is the height of the tree, due to the recursive call stack. This approach ensures that all edge cases are handled, such as when the tree is unbalanced or when x is the root or a leaf node. The code is efficient and concise, making it suitable for competitive programming scenarios like LeetCode. Here, we start by defining the structure of our Java solution. First, we declare two private variables, left subtree size and right subtree size, to keep track of the sizes of the left and right subtrees of the node chosen by player 1. Next, we define the helper method countNodes, which recursively calculates the size of the subtree rooted at a given node. If the current node matches the value x, we store the sizes of its left and right subtrees in the respective variables. The method then returns the total number of nodes in the subtree, which is the sum of the left and right subtree sizes plus 1 for the current node. This is a crucial step for determining the options available to player 2 and the overall tree structure. The tree game winning move method brings everything together. We start by calling countNodes on the root to calculate the total number of nodes in the tree and initialize the subtree sizes for the node chosen by player 1. Then, we calculate the size of the parent side, which represents all nodes not in the left or right subtrees of x or x itself. The condition for player 2 to win is straightforward: they must control more than half of the nodes in the tree. To determine this, we check if the largest of the three groups, left subtree, right subtree, or parent side, exceeds half the total nodes. Finally, we return the result of this comparison. This ensures that we account for all possible moves player 2 can make and correctly decide if they have a winning strategy. Here, we are given a simple binary tree with 7 nodes. The input specifies the root of the tree, the total number of nodes n, and the node chosen by player 1, which is x equals 2. The tree structure is laid out clearly, and our goal is to determine whether player 2 can win the game. First, we initialize 2 variables, self.left_size and self.right_size, to 0. These will help us keep track of the sizes of the left and right subtrees of the node chosen by player 1. We then start a recursive function, count_nodes, beginning at the root node, which is node 1. This function is designed to traverse the tree, count the nodes in each subtree, and store the sizes of the subtrees for the chosen node x. With the initialization complete, we move into the recursive traversal process. The traversal begins with the left subtree of node 1, which leads us to node 2. At node 2, we first traverse its left subtree, reaching node 4. Since node 4 has no children, the count_nodes function returns 1 for this subtree. Next, we traverse the right subtree of node 2, moving to node 5. Similarly, node 5 has no children, so count_nodes returns 1 for this subtree as well. With these results, we calculate that node 2 has a left_count of 1 and a right_count of 1. Importantly, since node 2 is the node chosen by player 1 x equals 2, we store these values in self.left_size and self.right_size. The total count for node 2 is then returned as 1 plus the sum of its left and right counts, which equals 3. Returning to node 1, we proceed to its right subtree, which is node 3. Node 3 has no children, so count_nodes returns 1 for this subtree. Combining the results, node 1 has a left_count of 3 and a right_count of 1. The total count for the entire tree is 1 plus the sum of these counts, giving us 7 nodes in total. With the total count of nodes established, we calculate the parent side size. This is the number of nodes that are not part of the left or right subtrees of node x, nor node x itself. Using the formula total_nodes minus the sum of self.left_size, self.right_size, and 1, we find that the parent_side_size is 7 minus 3, which equals 4. To determine the winner, we consider the maximum size among the parent_side_size, self.left_size, and self.right_size. Here, the maximum is 4, which exceeds n divided by 2, or 3. This means player 2 can control more than half the nodes and therefore wins the game. The output for this example is true. In the next example, we analyze a balanced binary tree where player 1 chooses the root node, x equals 1. This tree structure is perfectly symmetrical, with each node having 2 children until the leaf nodes. As before, we initialize self.left_size and self.right_size to 0 and begin the count_nodes function at the root. Traversing the left subtree of node 1 takes us to node 2. Node 2 has a left subtree of size 1 and a right subtree of size 1, giving it a total count of 3. Similarly, traversing the right subtree of node 1 leads to node 3, which also has a left_count of 1 and a right_count of 1, resulting in a total count of 3 for node 3. Back at the root node, we calculate that it has a left_count of 3 and a right_count of 3. Since the root node is the one chosen by player 1, we store these values in self.left_size and self.right_size. The total count for the entire tree is 7. Next, we compute the parent side size for this example. Using the same formula, we subtract the sum of self.left_size, self.right_size, and 1 from the total number of nodes. Here, the parent_side_size turns out to be 0, as all nodes are part of either the left or right subtree of the root, or the root node itself. To determine the winner, we again calculate the maximum size among the parent_side_size, self.left_size, and self.right_size. The maximum size is 3, which is equal to n divided by 2. Since player 2 cannot control more than half the nodes, player 1 wins the game. The output for this example is false. Now, we consider a skewed tree, where all nodes are aligned to the left. Player 1 chooses node 3 as x, starting with the initialization of self.left_size and self.right_size to 0, we begin the count_nodes function at the root, node 1. The traversal moves down the left side of the tree, reaching node 2 and then node 3. At node 3, we first traverse its left subtree, which is node 4. Since node 4 has no children, count_nodes returns 1 for this subtree. Node 3 itself has a left_count of 1 and a right_count of 0. Since node 3 is the node chosen by player 1, these values are stored in self.left_size and self.right_size. The total count for node 3 is then calculated as 1 plus the sum of its left and right counts, resulting in 2. Returning to the root, we find that the total count for the entire tree is 4. Finally, we calculate the parent side size for the skewed tree. This is the total _nodes minus the sum of self.left_size, self.right_size, and 1. Here, the parent _side_size is 4 minus 2, which equals 2. To determine the winner, we find the maximum size among the parent _side_size, self.left_size, and self.right_size. The maximum size is 2, which is equal to n divided by 2. Since player 2 cannot control more than half the nodes, player 1 wins the game. The output for this example is false. To analyze the time complexity of the tree game winning move function, we start by focusing on the count_nodes helper function. This function is responsible for traversing the entire binary tree to count the nodes. During this traversal, each node of the tree is visited exactly once. For every node, the function makes 2 recursive calls, one for the left child and one for the right child. This ensures that all nodes are covered, resulting in a total of n recursive calls, where n represents the number of nodes in the tree. For each node, the operations performed, such as checking if the node value equals x and calculating subtree sizes, are constant, or 1. Since the traversal involves visiting all n nodes and performing constant work at each, the overall time complexity is n. Now let's focus on the space complexity. This is primarily determined by the memory used for the recursion stack, as well as any additional variables in the function. The depth of the recursion stack depends on the height of the binary tree. In the worst case, if the tree is skewed, the height is equal to the number of nodes, n, meaning the recursion stack will use n space. In the best case, where the binary tree is perfectly balanced, the height of the tree is proportional to the logarithm of the number of nodes, log n, resulting in a recursion stack space of log n. Additionally, the function uses a constant amount of extra space for variables like left_size, right_size, and parent_side_size, which contributes only 1 space. Therefore, the total space complexity is n in the worst case and log n in the best case. Let's compare the current approach to a brute force or naive solution. A brute force method for solving this problem might involve explicitly simulating the moves of both players and evaluating all possible ways to partition the tree. This would require iterating over all nodes and their subtrees multiple times, leading to a time complexity of n squared. Additionally, such an approach would use more space to store intermediate results. In contrast, the current solution is far more efficient. By using a single traversal of the tree to compute the sizes of subtrees, the time complexity is reduced to n. The space complexity is also optimized to n, in the worst case or log n, for balanced trees. This makes the current approach not only optimal but also a significant improvement over the naive method. To better understand the performance of this approach, let's break it down into best, average, and worst case scenarios. In the best case, where the tree is perfectly balanced, the recursion depth is minimized to log n. The time complexity remains n, since all nodes are still visited once. In the worst case, where the tree is completely skewed, the recursion depth increases to n. Even in this scenario, the time complexity remains n, because every node is visited exactly once, though the space usage increases to n. For an average case, where the tree has a random structure, the recursion depth is typically proportional to log n, leading to a space complexity close to log n, while the time complexity remains n. Mathematically, the time complexity is derived from visiting n nodes and performing constant work at each, resulting in n*(1 equals n. The space complexity is determined by the recursion stack depth, which ranges from log n for a balanced tree to n for a skewed tree. In conclusion, the time complexity of the tree game winning move function is O(n), as every node in the tree is visited exactly once during the traversal. The space complexity depends on the structure of the tree, it is O(n), in the worst case if the tree is skewed in O log n, in the best case if the tree is balanced. This balance between time and space efficiency makes the current approach an optimal solution to the problem. Here are some common mistakes to watch out for in this problem. First, failing to calculate the sizes of the left and right subtrees accurately can lead to incorrect conclusions. This is critical because the game's strategy revolves around controlling larger portions of the tree. Next, it's important to understand that player 2 doesn't always need to focus solely on blocking player 1's immediate influence around node X. Instead, they can shift their focus to larger subtrees, which may offer a stronger strategic advantage. Another pitfall is overlooking edge cases, such as very small trees with only 1 or 2 nodes, or trees that are heavily unbalanced. Your logic must be robust enough to handle these scenarios. Additionally, mistakes in recursion or depth-first search implementation are common. If the base case or recursive logic is flawed, subtree sizes may be miscalculated. Lastly, assuming symmetry in the tree structure can lead to errors. Binary trees are often asymmetric, so strategies based on equal distribution of nodes between left and right subtrees are rarely reliable. Now, let's discuss some key interview insights for this problem. A crucial observation is that the challenge centers on maximizing the number of nodes player 2 can control. Once player 1 colors node X, the tree is divided into 3 distinct regions: the left subtree of X, the right subtree of X, and the remaining nodes, which include the parent of X and its ancestors. The optimal strategy for player 2 is to choose the largest of these 3 regions to maximize their control. This makes it essential to calculate subtree sizes accurately and efficiently. In terms of complexity, most interviewers expect an O(n) solution, where n is the total number of nodes in the tree. This is achievable by traversing the tree and computing subtree sizes using a single depth-first search. Finally, it's important to practice explaining your thought process clearly. Not only should you be able to calculate these sizes and evaluate player 2's options, but you should also be prepared to articulate your approach step by step. Clarity in communication is often as important as arriving at the correct solution. Let's take a look at some related problems and alternative approaches. For similar concepts, you could explore problems like LeetCode 543, diameter of binary tree, which involves finding the longest path between any 2 nodes, LeetCode 124, binary tree maximum path sum, which deals with identifying the maximum sum path in a tree, LeetCode 236, lowest common ancestor of a binary tree, focusing on finding the shared ancestor of 2 nodes, and LeetCode 114, flatten binary tree to linked list, which transforms a tree into a linked list. As for alternative approaches, you could try brute force, where for every node, you calculate the sizes of the 3 regions and determine the best choice for player 2. However, this is highly inefficient because it involves repeated subtree size computations, leading to an O(n)² complexity. A more practical solution is an optimized DFS, where a single traversal is used to compute subtree sizes and identify the best region for player 2, achieving an efficient O(n) time complexity. Another approach involves pre-computing subtree sizes using parent pointers, which allows for constant time queries. While this can be memory-intensive and less common in interviews, it's an interesting strategy to explore in certain scenarios. Great job! Before we wrap up, let's summarize what we learned. The binary tree coloring game teaches us how to analyze subtree properties and opponent strategies in combinatorial problems. If you enjoyed this session, don't forget to like, share, and subscribe for more tutorials. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!